So this is a video to help you study for your Chapter 10 test in statistics about regression. And the first problem says 20 different statistics students are selected randomly. Their body temperature is measured and their head circumference. So okay, so it says, what does R represent? That represents the sample value of the linear correlation coefficient. And what does rho represent? That represents the population value of the linear correlation coefficient. So R is a statistic that represents the value of the linear correlation coefficient computed from the paired sample data. Okay, so let me read through it all. R is a statistic that represents the value of the linear correlation coefficient. Alright, and rho is a parameter that represents the value of the linear correlation coefficient that would be computed by using all of the paired data in the population of all statistics students. Okay, now what I was about to say at first is, do you think there's really any relationship between someone's head circumference and their body temperature? Probably not. So the value of R would be estimated to be 0 because there's likely that there is no correlation between body temperature and head circumference. So there would be a correlation between body temperature and whether you have a fever, but not between, most likely not between your body temperature and your head circumference. And then in part C it says, does the value of R change if body temperatures are converted to Fahrenheit? No, because the value of correlation of R is, the value of R does not change because R is not affected when you convert values to a different scale. And so the second question says 20 students are randomly selected, and then if it is found that the linear correlation coefficient statistic R equals 0, does that actually indicate for sure that there is no association between the two variables? Well, no, it doesn't mean there's no association at all. It just means that there's no apparent linear association. So while there's no linear correlation, there could be a relationship that is not linear still. So remember, correlation, the value of R, is only talking about linear correlation. And then now we get to a problem with some data. So we're going to click on this icon. We're going to choose Open in StatCrunch. And then we're going to do Stat as usual. So one of the important things in statistics is knowing what kind of a problem it is. So we're doing a regression problem. That's how you can find what to do on the software. We're doing a simple linear regression, and then we have to know what the x variable is. So notice on the graph that the x-axis in all the graphs is internet users. So that tells us that internet users is the x variable. And the y variable is the award winners. And then let's look and see if there's anything else. So no, I think that's all. So we can click Compute. So let's look at these results. Oh, so actually, let's look at the graph first. So click on the arrow to go to see the graph. Now notice those three little dots. They make a unique pattern. So let's look for the scatter plot that has those three little dots like that. The only one that has them just like that is graph number B. So we use the graph in StatCrunch to help us recognize the correct graph below. And then we also look back with this arrow to find the linear correlation coefficient. Now the correlation coefficient is right here, so I'll copy that, and it says R, correlation coefficient, and I round it off to 3 decimal places, so 0.798, and then the null hypothesis and the alternative hypothesis, well, it depends on the question. So it says in the question, determine whether there is sufficient evidence to do what? To support a claim of what? Of linear correlation between the two variables. So the claim is that there is linear correlation. The null hypothesis would be that there is not correlation. So the null hypothesis is that rho, which represents the population correlation coefficient, is not there at all. So it's equal to 0. If there is linear correlation, then rho would be not equal to 0. Now notice this is a two-sided hypothesis. It means that there could be positive correlation or negative correlation. So when the question asks you to determine if there's evidence whether or not there is correlation, then you'll pick the one that says equal to 0 or not equal to 0. And then the test statistic, so the slope represents the estimate of the slope relating the variables together. So the t statistic, the t-test statistic that's next to the slope in the StatCrunch output, that's the test statistic that you need for this problem. So the test statistic is that, and 2 decimal places, it'd round off to 2.64, and then the p-value of that same test statistic, the p-value is equal to that, and that rounds up to 0.057. And then it says, because the p-value of the linear correlation coefficient is, okay, well, the significance level is 0.05, and 0.057, the p-value is bigger than that. So because the p-value is greater than the significance level, that means there is not sufficient evidence. There is not sufficient evidence to support the alternative hypothesis, which is the claim that there is correlation between the users and the award winners. Okay, then we do this problem in a very similar way. So we click that icon, click Open in StatCrunch, and then we go to Stat, Regression, Simple Linear, and then for the x variable, what do you think it is? Well, it would be the bill amount, the x-axis, and the y variable would be the y-axis, which is the tip amount. Now, I can also give you another way of knowing which one is which. So even if you didn't have the graph, you would know that the x variable, x stands for explanatory. So the x variable is used to explain why something else happens. So generally speaking, why would somebody give a tip that's bigger or smaller than somebody else? The main reason why, for most people, is their bill. So the explanatory variable is your bill. So if you have a large bill at a restaurant, like you've spent several $100s, then you would tend to give a bigger tip. So your explanatory variable is the bill, which predicts how big of the tip it will be. So the y variable is also called the dependent variable. Okay, now click Compute, and then there's the results. So let's look again at the scatter plot. So on this scatter plot, there's 3 little dots kind of in the middle like that, and then 2 dots kind of higher over at the end. So let's see if there's anything that looks like that on the options. So see those 3 little dots like that in the middle, and then 2 dots that are higher at the end? That one looks like this one. Now it doesn't quite look like that one because the other graph is squished together a little bit. So there we go, that looks a little bit more like it. So I would say graph number A is the only graph that looks just like that. Then let's find the linear correlation coefficient, R, from the sample. So I go back using the left arrow right there, and the linear correlation coefficient, R, is equal to that number. Now, one thing is if you are using APA format, for example, in psychological reporting, any number that cannot exceed 1, they'd usually leave off the number before the decimal point. So in some kinds of APA formatting, they might leave that 0 off. I'm not sure if you'll learn about that in your psychology research classes or not. So I need to round this off to 3 decimal places. So 0.863 would round off to 0.864 because of the 7 after the 3. And then determine the null and alternative hypotheses. So the null hypothesis, okay, well, it depends. It says determine if there is evidence to support the claim of a linear correlation. So once again, we are determining if there's any correlation, either positive correlation or negative correlation. So it could be, the null would have to be, therefore, that there is equal to no correlation, so rho would equal 0. The alternative would be that there's any correlation, meaning it either is positive or negative, meaning that it's not equal to 0. And then the test statistic, once again, would be right here. Round that off to 2 decimal places, so 3.43. The p-value is that number, 0.0266. And once again, in APA formatting, they would always leave the 0 off. That's before the decimal point because a p-value cannot be bigger than 1. So for this class, it doesn't matter. So 0.0266, that would round off to 0.027. And then it says because the p-value of the linear correlation coefficient is, let's find out. So the significance level is 0.05, and the p-value is less than that. So because the p-value of the linear correlation coefficient is less than or equal to the significance level, that means that there is sufficient evidence to support the claim that there is a linear correlation between the bill amounts and the tip amounts. And then now it asks this. This is kind of a surprising question. If everyone were to tip with the same percentage, then R equals what? Well, if everybody always tipped the exact same amount, let's say 20%, then the correlation would be perfect. There'd always be a perfect relationship between the bill and the tip. Now, when I say perfect, that's not necessarily actually perfect, because this means that there wouldn't be any nice people in the world who might give you an extra tip. So for some people, the thing that they enjoy the most about going to the restaurant is giving somebody a nice tip at the end. They enjoy that even more than the food that they're eating. So those people wouldn't be there. So it doesn't really mean that it would be a perfect situation if everybody tipped the same percentage. It just simply means that there would be a perfect correlation of 1 if everybody tips the same percentage. Okay, what is a residual? A residual is an important concept. So remember, when you're predicting something with regression, you're trying to do something like predict the tip that somebody will pay. Well, usually, in fact, most of the time, a prediction is slightly wrong. So the truth is actually more important than just merely the prediction. So truth comes first. And if you take the true actual value that's observed minus the predicted value, that's defined as a residual. So a residual is a value of the true y value, which is simply called y, or the observed value of y, minus y hat. Y hat means not the real y value, but just the predicted y value. So if you have an observed value if you have the difference between an observed value of y and a predicted value of y, which would be the true y minus the predicted y, that's called a residual. And then question B is also an important thing. In what sense is the regression line the straight line that best fits the points in a scatter plot? Well, the regression line has the property that the sum of the squares of the residuals. So if you've measured all the errors between the true values and the predicted values, some of them would be negative and some of them would be positive. So if you added them up, they would actually add up, they'd cancel each other out and you get 0. So that wouldn't help. So you square them so that you can really figure out the total amount of all the errors there are. And then you want the errors in your prediction to be as small as possible. So you want to have the sum of the squares of the residuals, which represents the errors in your predictions, to be as low as possible. Okay, then finally this last question. This last question is kind of tricky, so pay close attention. So once again, we're going to open the data in StatCrunch. And then stats, regression, simple linear. Now there's one thing different about this problem. So the x variable, it specifically says the right arm is to be the predictor variable. So the right arm is the predictor variable, the left arm is the dependent variable. And then it also says in part B, try to predict if the right arm has a pressure of 100, try to predict the pressure in the left arm. So what we're going to do is scroll down, we're going to plug in an x value of 100, or whatever your problem says, in part B. So it says predict if the right arm is 100, so we're going to plug in an x value of 100 into that. Now click compute. Okay, so we're going to use this to put together a formula for the regression equation. The formula for the regression equation is equal to the intercept. It's just like college algebra. You take the intercept of the line by itself and you round it off to 1 decimal place, so it's just 48.4. 48.4. And then you use the slope. So the slope of a line is the value that goes beside the x in the line. Like remember y equals mx plus b? The number m is the slope and it goes beside x. So we're going to take that slope and put it beside x, then round it off to 1 decimal place. So it'll be 1.2. That's the equation. Now the prediction comes next. Now be careful, don't hurry through this too fast. So the predicted value is this. So at first I'm going to put that number in, but that number is not for sure going to work in your problem. So don't submit the test yet. Okay, so what we need to find out is we need to find out if this regression equation is actually trustworthy. So this is one thing many people in the news and everywhere they do is they use statistics in a wrong fashion. They use them and use them and use them to predict everything, but they don't actually test to see if it's reliable and let alone whether it's actually valid. Okay, so let's just look real carefully. Let's look at the value of R. Okay, so how many data points do we have? How many pairs of data points? We have one person with a right arm and a left arm. That's 1, 2, 3, 4, 5. Okay, so we have 5 data points. So click on this icon. Now look at the value of n equals 5. Okay, now also look at the significance level. That's 0.05. So we need n equals 5 and the significance level is 0.05. So n equals 5, the significance level is 0.05 right there. And the value of R that we need in order for this to be a reliable equation, the value of R has to be at least equal to or greater than 0.878. So let's see if it is. 0.878. The value of R is only 0.848, which is less than 0.878. So our correlation coefficient is not big enough and strong enough. It's not large enough. It's not close enough to 1 or -1 to be a to be a somewhat perfectly strong relationship. So since this value of R is not big enough to be reliable, because this is the minimum value that's reliable, that means we cannot use this equation to make predictions with. So 0.848 is not big enough to be bigger than or equal to 0.878. So that means as honest statisticians, which there are not very many of them, we cannot use that equation to predict anything with. So then you might ask yourselves, well, how in the world do we predict it? Well, we just go back to the most honest thing to do is just go back to the old-fashioned way. We cannot use this number 165. So erase that number. And what we do is we're trying to predict the pressure in the left arm. So all we need to do is just predict the pressure in the left arm by finding the average pressure in all of the left arms. So what we're going to do is open the data up in StatCrunch again. So open it in StatCrunch. And then go to Stats, Summary Stats, Columns, and then find the left arm, which is what we're trying to predict, and then just click on Mean. So we'll just find the mean or the average of the left arm, and the mean of the left arm is 156. Just 156. So you could round that off to 156.0. So given this blood pressure in the right arm is 100, the best predicted blood pressure in the left arm is 156.0. The best predicted blood pressure in the left arm is 156.0. So remember we got something like 165 from the equation, but that prediction is invalid because that regression equation doesn't really have enough reliability in it. So we're just going to predict the blood pressure in the left arm by finding the average blood pressure in the left arm. There we go. So submit test. And those are your notes for your Chapter 10 test. And good luck to you, and keep up your wonderful work. You're doing amazing.